The purpose of this short video is to describe how to account for gravity when thinking about the functions of the cardiovascular system. You may recall that in an earlier video I said that when we ignore gravity, blood flows in the cardiovascular system from high to low pressures. So in this video we're going to stop ignoring gravity. Gravity becomes particularly important when we're thinking about posture changes, and we'll look specifically at posture changes in a moment. Let's start by thinking about the supine, or the lying down position. So in this case, it's usually reasonable to ignore gravity. That's not a perfect assumption because there's a height difference from the top side of the body to the bottom side of the body when someone's lying down, but ignoring gravity is not a bad assumption here. So when we report these kinds of pressures, say 100 millimeters of mercury in the large arteries and 5 millimeters of mercury in the large veins, we're thinking about the supine position. Blood moves from the high pressure down to the low pressure. And then there's a pump that pumps it back up to the high pressure, like so, and blood moves around the circuit. Okay, so now what happens when you stand up? That's when we have to really start thinking about gravity. So remember, in the supine position, there's not much of a pressure drop in the large arteries or the large veins. The pressure in the large arteries in the leg is roughly the same as it is back at the level of the heart. The pressure drop happens in the arterioles and the microvascular network, which in this diagram are somewhere here. So when you stand up, there's a column of fluid pushing down on the blood in your feet. What is the pressure imposed by gravity? Well, remember, mercury is about 13 times more dense than blood or water, so we can estimate, say, 150 centimeters of water, rough estimate, divided by 13 centimeters of water per centimeter of mercury equals around 10 or 11 centimeters of mercury, or around 100 millimeters of mercury. So the pressure difference in the large arteries at the bottom of the body becomes something like 200 millimeters of mercury, and so blood is moving from a lower to a higher pressure. How can that happen? Because gravity is working against the pressure drop. Or you can say that the pressure drop is balanced by the gravitational force. The end result is similar to what we had over here on the left. No resistance in the large vessels means no drop in the driving force along the arteries. Okay? On the right, in a standing position, the 100 millimeter of mercury pressure difference driving the blood up is balanced by the 100 millimeters of mercury of gravity pushing down. So the pressure drop across the microvasculature might be the same here on the right as it was on the left, and you would have a venous pressure here of something like 105 millimeters of mercury. So there is a very large pressure drop from the veins in the feet back up to the heart. But here, that pressure drop is working against gravity. So using the same kind of logic, this is what would tend to happen to the pressure above the heart. A 95 millimeter of mercury pressure drop from the large arteries to the veins results in a venous pressure of minus 35 millimeters of mercury, and the gravitational force down is balanced by a pressure force up. Okay, that all makes sense, but it's all wrong. Okay, or more specifically, there's more to the story. Okay, so this here, what I'm showing on the right, is all what would happen if your cardiovascular system were made out of rigid pipes, like the plumbing in your house or your apartment building. But you're not made out of rigid copper pipes, and there are reasons why the pressures don't ultimately look like this. Okay, so first off, let's look at the brain. Okay, so this kind of negative pressure causes vessels to collapse, and collapsed vessels have high resistance, and that's exactly what happens. Specifically in the brain, upon going from the supine to the standing position, the internal jugulars collapse, greatly increasing resistance and rerouting the venous flow largely to the vertebral venous plexus. The overall result is a venous resistance that opposes the gravity force. So one of the consequences of that is that the overall driving force for cerebral blood flow is reduced. Instead of a 95 millimeter mercury driving force from the large arteries to the large veins, like we had lying down, here there's only something like maybe a 55 millimeter of mercury driving force. So the brain responds to that reduced driving pressure by dilating the cerebral resistance arteries to maintain normal flow. That process is called myogenic autoregulation. Okay, so what's happening below the heart? So this is a nice figure from this textbook. So first, let's look at what happens without compensation, which is illustrated here. The numbers here are slightly different than the ones we just worked out, but roughly the same. There's a roughly 100 millimeter of mercury increase in arterial pressure and venous pressure down here in the feet and the legs. And so in the feet and the legs, that would mean a huge increase in venous blood volume and infiltration of fluid out of capillaries. So here, we're illustrating what happens as a result of sympathetic stimulation kicking in. So why do the sympathetics kick in? Well, with this big shift in blood volume to the lower half of the body and the veins, and with the pressure drop in the arteries above the heart, for example, the carotid sinus, we have a barrel reflex mediated increase in sympathetic drive. You get an arterial pressure drop due to an increase in arterial resistance down here, and increase in venous tone, squeezing volume out of the veins. Next thing to consider is that standing also requires skeletal muscle contraction that's associated with further squeezing on the vessels, which is illustrated here. So the overall result is that capillary pressure might be elevated. So maybe taking these numbers, 40 millimeters of mercury in the standing position compared to 25 millimeters of mercury in the lying down position, but that's a great deal less than what you have without compensation. So that means we still have net filtration driving fluid out of capillaries. Okay? And you might notice if you're standing on your feet if you're standing up on your feet all day, your feet might get swollen a little bit. But also notice that in this compensated state, we have a pressure drop in the veins that's not enough to overcome the 100 millimeters of mercury gravitational force driving blood down. So to compensate for that, there's a system of valves in the veins that work in concert with contracting skeletal muscle, the so-called skeletal muscle pump, which drives flow back up to the heart. So that, in a nutshell, is how to think about the major cardiovascular compensations to gravity.